Hi friends, in this video we are going to discuss about characteristics of an alternator. What are the different characteristics of our alternator? Let's see. In that, the first characteristics is open circuit characteristics. Open circuit characteristics. This is simply called as OCC. And next one, short circuit characteristics. Short circuit characteristics simply called as SCC. Let's see these two characteristics first of all. Here, open circuit characteristics are drawn between field current and induced EMF. By changing the field current, what is the change in EMF? We have to draw the graph, plot the graph. And short circuit characteristics are drawn between field current and armature current and EMF. Open circuit voltage, short circuit current. By changing the excitation. This is simply here. For example, we have an alternator like this. The alternator armature is open circuited. This is open circuited. There is no connection of load. Then we have to calculate the EMF developed here by changing the excitation. Here the current flowing in this is a field current. By changing the excitation, we have to calculate the EMF on open circuited alternator. Whereas here, for example, this is my alternator. We have to short circuit this alternator, short circuit this armature winding. And by changing the excitation, nothing but the field current, we have to calculate the current flowing in this short circuited armature. This is the short circuit test and this is the open circuit test simply called. Are you okay? Getting or not? Are you ready? Right, let's draw the graph. Here, take the graph and here on y-axis field current or excitation, on x-axis field current or excitation, on y-axis EMF. When excitation is 0, then the field current is 0, then the EMF also 0. But when excitation increases, nothing but when field current increases, then flux increases. If field current increases, nothing but flux increases. If flux increases, nothing but ultimately EMF increases. So let's increase the EMF. Up to some point, this curve is linearly increases. But after some point, that point is called saturation point, or that point is called knee point. After that point, it goes into saturation. This is the open circuit characteristics. The open circuit characteristics are up to saturation point, it is a linear curve up to saturation point. Then after it goes into saturation. This is our open circuit characteristics. For example, if you draw a tangent to this curve, if you draw a tangent to this curve, this tangent is called air gap line. This is called air gap line. Are you getting or not? This is called air gap line. Right. Now, for example, this is the rated voltage or open circuited voltage. At this rated voltage condition, the field current is taken as IFOC. IFOC is nothing but the required field current to produce the rated voltage. The required field current to produce the rated voltage on open circuited armature of alternator. What I said you, the required field current to produce the rated voltage on open circuited armature is called this IFOC. This is generally the open circuit test. And in generally, this IFOC is very high. At maximum field current only, we can get the rated voltage on open circuited armature. Sir, if the field current increases, what happens, sir? There is no major problem, but there is a problem of saturation. That's it. Is it okay? Clear? This is the open circuit test or open circuit characteristics. Let's go for short circuit characteristics. In short circuit characteristics, the plot is drawn between excitation and our armature current. Our armature current. When the excitation is 0, then there is no armature current actually. When excitation increases, then ultimately our armature current also increases linearly. This is linear, exactly, perfectly linear curve. This is non-linear curve, but this is perfectly linear curve. For example, this is my rated armature current. At that condition, the field current is taken as IFSC. IFSC. What is IFSC? The IFSC is nothing but the field current required to produce rated armature current on short circuited armature. What is that? The required field current to produce rated armature current on short circuited armature. Are you okay? And also this is also called the field current required to compensate. The field current required to compensate drop due to armature reaction and drop due to leakage flux or leakage reactance. Drop due to armature reaction and drop due to leakage reaction, leakage reactance. This is the field current required. Yeah. What about final conclusion of these two? Open circuit test gives us voltage, short circuit test gives us the current. And here the open circuit characteristics is non-linear characteristics, but short circuit characteristics exactly linear characteristics. Now compare to these two characteristics in which we required less field current, in which we required more field current to get the rated values. Tell me. Generally in short circuit we required less excitation. In open circuit we required more excitation. Here more field current and here less field current. Less field current with less field current. Right? So generally here the maximum flux density and here minimum flux density, maximum flux density and here minimum flux density. When we can get the minimum flux density, in generally During the magnetization or during the demagnetization? Tell me. At what condition we can get the minimum flux? Tell me. Tell me fast. Yeah, minimum nothing but there is a demagnetizing effect. If there is a magnetizing effect, the flux is maximum. If there is a demagnetizing effect, the flux is minimum. So, under short circuit condition, the alternator armature reaction is pure demagnetization. What is that? Pure demagnetization effect of armature reaction. Pure demagnetization effect of armature reaction will take place at short circuited condition. Pure demagnetizing nothing but what is the load? What is the angle between EMF and the armature current? Exactly. What is that? Pure demagnetization, nothing but zero power factor lagging. The alternator, armature current and EMF displaced by 90 degrees lagging. Nothing but here zero power factor lagging. Zero power factor lagging. Sir, now tell me, what is the armature reaction here? In short circuit condition, the armature reaction is pure demagnetization. Now tell me, what is the armature reaction here? Some fellows telling that pure magnetization. Who said that answer pure magnetization? They are eligible for Nobel Prize. Okay. You fellow, this is open circuit. At open circuit, what is armature current? If armature current is zero, what is armature flux? If armature flux is zero, what is the effect of armature flux on main field flux? What is the effect of armature flux on main field flux? There is no effect because there is no armature flux. So, tell me. So, no armature reaction. There is no question there is no question at all. So there is no armature reaction, but here we have a armature reaction that is pure demagnetization. Pure demagnetization. This is what the open circuit test and short circuit test of synchronous meshing, or simply open circuit characteristics and short circuit characteristics of our synchronous meshing. Are you getting or not? Right? Clear? Right. We are going to discuss about zero power factor characteristics and load saturation characteristics. Here, the zero power factor characteristics are drawn at zero power factor lagging, at zero power factor lagging load. These are drawn at all the power factor, different power factors. And in both the case, we have to maintain constant speed. We know that constant speed. And here, the zero power factor characteristics are drawn between V and IF, IF and V, or V and IF at zero power factor lagging, and these are drawn between IF and V at all the power factors. Let's see how it is. See, this is the excitation and this is the voltage V at zero power factor. Zero power factor lagging, nothing but short circuited condition. Yes or no? I said you already. So this is the field current required to compensate armature reaction drop and leakage reaction drop, that is IFSC. From here we have to draw the curve. This is ZPF characteristics. This is zero power factor characteristics. For example, if you draw the open circuit characteristics, the open circuit characteristics are like this. This is the open circuit characteristics and this is the short circuit characteristics. For example, if this is the rated voltage, For example, for example, if this is the rated voltage, if this is the rated voltage on my open circuit characteristics, and if you take a projection here, and for this if you draw like this, they will ask you question what it represents. Here at this, what this represents, they will ask you question like this represents that the drop due to leakage reactance. This represents the drop due to leakage reactance, IAXL. This is called IAXL drop. This represented in ZPF characteristics. This is important. And actually, I said you already, what is IFSC? IFSC nothing but the field current required to produce rated armature current on short circuit armature. Very good. But this is also the field current required to compensate drop due to armature reaction and drop due to leakage reactance, drop due to armature reactance and leakage reactance both. This is also same. I will explain you in ZPF method. Up to now, just remember, this is characteristics drawn at 0 power factor lagging between IF and V. At 0 power factor lagging, this is ZPF characteristics and this is OCC characteristics, and at rated voltage, this difference is equals to leakage reactance drop. And here this represents the field current required to compensate, drop due to armature reactance and leakage reactance. This is simply the ZPF characteristics. Right? And next one, load saturation characteristics. What is load saturation characteristics again? The load saturation characteristics again drawn between IF and V. Again, IF and V. We know that generally from here, this is ZPF lagging, and this is some 0.8 lagging, and this is some 0.6 lagging, like that. This is at unity power factor, the curves when the changes, and this is 0.8 leading, and this is 0.6 leading the curve, and this is 0 power factor leading the curve. Here, what is the purpose of load saturation characteristics? For example, I am taking, this is the rated voltage. For example, this is the rated voltage, and let's see here, this is the rated voltage. See, for 0 power factor leading, the field current I am taking is IF1. For unity power factor, I am taking IF2. For 0 power factor lagging, I am taking IF3. Which field current is more? The IF3 is greater than, IF2 is greater than IF1. Nothing but to get the rated voltage, in leading we required less field current, but in lagging we required more field current. More field current bole to under excitation or over excitation? Lagging nothing but over excitation, leading nothing but under excitation, because less field current required more field current required, normal field current required normal excitation for unity power factor. The field current required for leading is less, under excited. For lagging is more, over excited. For unity power factor, normal excited. This represents the load saturation characteristics. This is simply about ZPF characteristics and load saturation characteristics. Understood? We are going to discuss about external characteristics and compound characteristics. Let's see, generally the external characteristics are drawn between V and IA, and the compound characteristics are drawn between IF and IA or IA and IF. These are the compound characteristics and external characteristics. See here, draw the compound characteristics how they are. Here we have to take IA, nothing but load, and here V, and here we have to take IA and here IF, IA. See here, when IA is 0, generally what is the formula? E is equals to V plus IAZS. V plus IAZS. If IA is equals to 0, V is exactly equals to E. If IA is equals to 0, V is equals to E. Nothing but when IA is 0, this value is equals to E. Then after, when IA increases, based on load, if it is leading load, then the voltage increases like this. For example, this is 0.2 leading, this is 0.6 leading, this is 0.8 leading, like this. Sorry, this is 0.8 leading, this is 0.2 leading, and this is 0 power factor leading, like this. Otherwise, if it is lagging load, then the curves are like this. If it is lagging load, 0.8 lagging, or 0.6 lagging, 0.2 lagging, like this. This is different plots. At voltage and IA, these two are represented in this plot. From this we can define voltage regulation also. What is voltage regulation? Voltage regulation is equals to E minus V upon V. For example, if E is exactly equals to V, voltage regulation is 0. Yes or no? For example, if this E is less than V, nothing but E is, this is V, this is load voltages, but this is no load voltage. Here V is greater than E, In this case, the EMF is less than V. If EMF is less than V, then our voltage regulation is negative. This is negative voltage regulation. We know that in leading we can get the negative voltage regulation. As well as, for example, if this E is greater than V, then voltage regulation ultimately positive. See here, this is no load voltage and these are the full load voltages. Here the no load voltage is greater than the full load voltages. So here the voltage regulation is positive. For lagging, voltage regulation is positive. For leading, voltage regulation is negative. From this plot we can derive these points. This is for external characteristics. External characteristics are drawn between V and IA. This is same even in DC machine also. External characteristics decided by V and IA, and they gives about voltage regulation. This is clear. Next one, compound characteristics. Same as usually, the compound characteristics also say for lagging load, it requires more field current, and for leading load, it requires less field current. For leading load, less field current. For lagging load, more field current for rated values. In general thing, this is compound characteristics are similar to load saturation characteristics, right? And this is external characteristics. These are the completely what is characteristics of an alternator. Here the characteristics we saw: open circuit characteristics, short circuit characteristics, zero power factor characteristics, and load saturation characteristics, and external characteristics, and compound characteristics. Tell me, OCC characteristics are drawn between field current and excitation. Short circuit characteristics are drawn between field current and armature current. And ZPF characteristics are drawn between exactly field current and voltage. Load saturation characteristics also field current and voltage, but this is at zero power factor lagging. External characteristics are drawn between V and IA or IA and V, and these are drawn between IF and IA. You should remember all this. And here, these are very important for our next analysis. Okay? So, now you have a question, sir, what is the purpose of these characteristics? Up to now, I explained you about voltage regulation and condition for maximum voltage regulation, condition for minimum voltage regulation, that is a direct voltage regulation method. But that direct voltage regulation method is used for normally low rating machines. For high rating machines, the direct voltage regulation method is not preferable at all. For high rating machines, we have a indirect voltage regulation methods. So for that indirect voltage regulation methods, we need these characteristics. By using these characteristics, we can find voltage regulation for large rating machines. For large rating machines, we can find the voltage regulation. Understood? The purpose of characteristics is to find the voltage regulation indirect method, right? By using OCC characteristics and SCC characteristics and zero power factor characteristics, what we have to do? We have to find the voltage regulation of large transformer, large alternators, voltage regulation of high rating alternators, high rating alternators. For that we have some methods. What are those methods? First one, EMF method or synchronous impedance method. And second one, MMF method or ampere turns method. Ampere turns method. And next one, ZPF method or Portier triangle method. What is that? EMF method, MMF method, ZPF method, and fourth one, ASA method, American Standards Association method. These are four. And fifth one, saturated synchronous impedance method. Saturated synchronous impedance method. These are the 5 methods to find the voltage regulation of high rating alternators. These 5 methods are called indirect voltage regulation methods. Indirect voltage regulation methods. Indirect voltage regulation methods. These are the 5 methods. EMF method or synchronous impedance method, saturated synchronous impedance method, ampere turns method, Portier triangle method, American Standards Association method. We have to see everyone, each and everyone now. Getting or not? Right? Thank you.